Paper 2, May 2019, AS. Question 1. The structures of 3 organic compounds A, B and C are shown below. So remember, these are skeletal formulas. So at every point here, then there's a carbon with some hydrogens as well. So I've got a carbon here with a double bond O. Going to another carbon here, I've got a CH3 here. So this is a ketone. Here I've got a carbon with a double bond O and an OH, I've got a carboxylic acid. And here I've got a ring and I've got a carbon with a double bond O and an H. I've got an aldehyde here. So I've got a ketone, a carboxylic acid and an aldehyde. Now I've got to distinguish between them. So how do I distinguish between A and B, a ketone and a carboxylic acid? The easiest way is to test for a carboxylic acid by adding something like sodium carbonate. Observation with a ketone, no change, no reaction. Observation with B is that I'm going to get bubbles. Compounds A and C, so between the ketone and the aldehyde, I could add something like warm Tollens reagent or Failing solution. I'd get no reaction, I'd see no change with the ketone, but with the aldehyde I'd see a silver mirror if I'd chosen to use warm Tollens, or I'd see a brick red solid, a brick red precipitate if I'd decided to use Failing solution. Outline the mechanism. So I've got bromoethane here and I've got potassium cyanide making propane nitrile and potassium bromide. But remember, in the mechanism, potassium cyanide dissolves in the water. So we use something like methanol and water as a solvent here, and it will make Cn- with a lone pair of electrons, and it's that you've got to use. The K is a spectator ion. Don't include the K in the mechanism at all. I've got a Cn- ion, I've got a lone pair of electrons on the carbon of the Cn. That will attack the delta plus on the C, on the polar bond between the C and the Br. Remember, the Br is electronegative, so it gets a small minus charge, and the C gets a small plus charge, delta plus and delta minus, so I've got a polar bond here, and the lone pair of electrons attacks or bonds to the carbon of the CBr. The electrons then go from the CBr bond onto the Br. So the Cn then bonds to the C, so I end up with CH3, CH2, Cn, and the Br gets a minus charge because it's had electrons moved onto it. The Cn part doesn't have a charge because it's had electrons move away from it. Give the name of this compound here is propane. Remember, there's a carbon there, 1, 2, 3, so it's propane, single bonds, and an N is a nitrile, propane nitrile. Calculate the percentage atom economy for the formation of D in this reaction. So what I do is I look at the desired product, which is this that I'm making, and divide by the MRs of all of the products. So percentage atom economy is the MR of the desired products divided by the MR of all the products. So the desired product here, I've got 3 carbons, each 12 is 36, hydrogens, 5 ones is 5, and 14 for the nitrogen, and then all of them is that again, plus the sorry, I'm doing it from here, from the KBr. So the KBr, the K is 39 and the Br is 80. So in this reaction, the mass, the MR of the propane nitrile is 36, add 5, add 14, and the mass of everything on the right hand side is 36 plus 5 plus 14 plus the K, which is 39, plus the Br, which is 80. And I work that out and it'll come out as 55 divided by 174 multiplied by 100%, 31.6. I've put it to 3 significant figures. It says the appropriate number of significant figures. I've decided to use 3 significant figures because most of my MRs will be or could be to 3 significant figures. Question 3. A student determined the enthalpy of combustion of cyclohexane. So let's have a look what we've got in the question. We've got 50 grams of water being heated by cyclohexane being combusted or burnt. We've got the initial temperature of the water, we've got the amount of fuel being burnt if we subtract those 2 numbers, we've got an enthalpy change for burning 1 mole, so in kilojoules per mole, so the kilojoules of energy that are released from burning 1 mole of cyclohexane. We've got specific heat capacity, and we've got the relative formula mass of the cyclohexane, 84.0. So we're looking immediately at using delta H equals minus mc delta T, or Q equals mc delta T. I always put the minus in and use delta H equals minus MC delta T, because that gives you the enthalpy change, the heat energy released, which should then match the minus value on the enthalpy of combustion, because combustion is an exothermic reaction. Now we know that delta H is minus 1216 kilojoules per mole. So what that means is that when you burn 1 mole of the fuel, that's the amount of heat energy that you get released per mole. So I'm getting 1216 kilojoules of energy if I burnt 1 mole of the fuel. So the actual mass of the fuel burnt, if I subtract the two numbers from here, so the initial mass and the final mass, I can work out that I've got 0.63 grams of the fuel burnt. So the MR of the fuel is 84, so moles is mass divided by MR, 0.63 is the mass burnt divided by 84. I've used up 0.0075 moles of the fuel. So now I've got the amount of number of moles of fuel that I've burnt. If 1 mole of a fuel releases 1216 kilojoules of energy, then 0.0075 moles releases 1216 multiplied by 0.0075. It releases minus 9.12 kilojoules of energy. Now, the kilojoules needs converting into joules for this equation here, so delta H here is in joules. So I'm going to multiply by 1,000, so it's 9,120 joules. So that's the amount of energy in joules that will be released or should be released by the amount of fuel that I've got burnt. So I can put this into my equation now. So this is the heat energy that should be released in my experiment. 50, remember, 50 is the mass of the water being heated up, so M is 50 grams. So this M here is the mass of the water being heated up, nothing to do with the fuel at all. 4.18 is the heat capacity, specific heat capacity of the water, you'll always be given that, and delta T is what we've got to try and work out, so that's the heat change for this reaction. If I multiply these two together, and then 9,120 divided by 50 multiplied by 4.18 comes out as 43.6. I've got a minus on this side and I've got a minus on this side, so I've got a minus divided by a minus, so it's a plus value. That's correct, because the heat change, the temperature change will be a positive value, because the temperature is going to go up as I burn a fuel underneath the beaker. So that's correct. Now what it wants to know is what the final temperature is. So I've got the temperature change here. The initial temperature was 19.1. It's gone up by 43.6. That's been the change. So if I add these two together, it's gone up to 62.7. I've decided to use it to 3 significant figures because in my question here I've got something to 6 significant figures, but I'm always looking to find the lowest number of significant figures. 84.0 is 3, 4.18 is 3, 50.0 is 3, 1216 is 4. The masses here are to 6, the initial temperature is to 3, so I always take the lowest number of significant figures in my question, which is 3, and that's why I'm putting this to 3 significant figures. A data book value for the enthalpy of combustion is minus 3920. The student concluded the temperature rise recorded in the experiment was smaller than it should have been, suggest a practical reason for this. So the enthalpy change should be higher than it is. The reason is that you've got heat loss to the surroundings. Other reasons are that the fuel didn't fully combust, incomplete combustion, and the vessel might actually heat up, so the beaker might heat up as well, absorb some of the heat instead of that being registered on the thermometer. Table 2 gives some values of standard enthalpies of combustion here. So I've got standard enthalpies of combustion. Use the data to calculate the enthalpy change for the reaction represented by this equation. So I need to use Hess's law here. So I've got to work out the enthalpy change for this reaction. Now the enthalpy change is independent of the route taken, so I've got some other equations here. I've got some other enthalpies of combustion, and I can come around this way, and by adding all of these together I can work out this enthalpy change. So carbon going to carbon dioxide, so enthalpy of combustion will be carbon being burnt in oxygen to make carbon dioxide is minus 394, but that's for 1 1 carbon, and I've got 6 here. So to turn carbon into carbon dioxide, enthalpy of combustion, it's 6 multiplied by 394, which is minus 2364. Remember, the minus has got to stay in place because it's releasing energy. I've got the enthalpy of combustion of hydrogen. Hydrogen and oxygen are going to make water. But again, I've got 6 H2O and I've got 1 H2O here, so it's minus 286 multiplied by 6, which is minus 1719. And I've got the enthalpy of combustion of the cyclohexane, C6H12, going to form the carbon dioxide and water. I've got this one here. Now I've only got one of these and I've got one of these here, so minus 3920 is correct in this direction. Now then, I've got this equation, and it's come from here to here, here to here, and it's got to go from here back to here to match that one. So if I'm going in this direction here, all these arrows have got to come in this direction, so I've got to reverse that sign. So this one, this one is minus 2364. I've done that, it's in the right direction. Minus 1716, it's going in the right direction here, but this one needs reversing. Doesn't need multiplying by anything, because I've got 1 cyclohexane, I've got 1 cyclohexane here, but it does need reversing, so that should be a plus 3920 to come round in this direction. So I've got minus 2364 minus 1716 plus 3920. I've got equals, and this will be in joules. So and then I divide by 1,000 to get it into kilojoules, because it asks for it in kilojoules, or actually it doesn't ask for it in kilojoules, so you could leave it as 160,000. I could leave it as let's just have a quick look. Oh, sorry, all of these in kilojoules anyway. Sorry, all of these are in kilojoules anyway. So minus 2364 minus 1716 add 3920 comes out as 160 anyway. So I don't need to do any conversion. It's not specified what kind of units it's going to be in. And if you look in the equation in the table here, it says kilojoules per mole. So it just comes out as minus 160 kilojoules per mole. So that's fine. We'll just leave it as it is. Question 4, 4.1, it's about fossil fuels. The petrol fraction from the crude oil contains octane. Give an equation for the complete combustion of octane. So octane here in the question tells you is C8H18. Combustion is a reaction with oxygen. We'll balance that in a moment. Complete combustion of octane, so it makes carbon dioxide and water. Incomplete combustion would make carbon monoxide and water, or possibly even carbon and water if it was really incomplete. But it's complete combustion, so it's making CO2 and water. Now what I would always do is I would look to see if balance the carbon, say for example. So carbon appears here and it only appears in one of the two, so products, that is. So carbon appears in one of the two products, hydrogen only appears in one of the two products, but oxygen appears in both the products. So don't balance the oxygens first, do the carbons and the hydrogens that only appear in one product, and then do the oxygens last. So I've got 8 C's, so I've got 8 CO2s. I've got 18 hydrogens, so I must have 9 waters, 9 2s are 18, and now I can do the oxygens last of all, so I can add up these in here. 8 2s are 16, add 9 is 25, so I'm going to need 12.5. 12.5 times 2 is 25. The combustion of petrol in car engines producing a pollutant nitrogen monoxide. Give an equation for the reaction that removes nitrogen monoxide in a catalytic converter. So what a catalytic converter is, it removes 2 very poisonous gases, nitrogen monoxide and carbon monoxide. So if I get any of the petrol that is incompletely combusted, so incomplete combustion in a car engine, that's likely to happen, remember, because you haven't got a plentiful supply of oxygen coming into a car engine. There's a limited supply, so I'm going to make some carbon monoxide due to the limited supply of oxygen coming into a car engine. So I've got to get rid of those 2 gases that are poisonous, the nitrogen monoxide and the carbon monoxide, and they come together to make nitrogen, which is a gas that's abundant in the air, so about 79% of the air is nitrogen anyway, so that's fine, and some carbon dioxide, which isn't great because it's a greenhouse gas, and we know that carbon emissions from car engines make carbon dioxide. Hopefully the carbon monoxide will be removed by the catalytic converter. So I've got nitrogen monoxide NO, CO makes N2 and CO2. I've got to then balance it. I've got two N's, so two NOs. Again, balance the N's and the C's first. Leave the O's until the end, because there's more O's. The O's appear in both of these reactants. So do the N's first. N2, two N's, two NO. I've got CO2, so I'm going to need two CO2s to balance up the oxygens to make four oxygens, two CO2s. Sulfur dioxide is produced in the combustion of fossil fuels because there's some sulfur content in things like coal and oil. The total emissions of the sulfur dioxide in the UK have been fallen dramatically. Okay, sulfur dioxide is now removed from the flue gases. A flue means a chimney, so the chimney gases in power stations by reaction with calcium oxide. So calcium oxide absorbs any sulfur dioxide that might be released and cause acid rain. In 1970, the total UK emissions of sulfur dioxide was 63.49 million tonnes. So the only problem with this question is that you're dealing with big numbers, and it tells you here that 1 tonne is 1,000 kilograms. So 6.49 million tonnes. I've got 6.49 million multiplied by 1,000, and it's in kilograms as well. So I'm dealing with very, very big numbers. Apart from that, the calculation is not too bad. Calculate the mass in kilograms of calcium oxide that would need to react with this mass of sulfur dioxide. Give your answer in standard form. So let's start to work out the number of moles of sulfur dioxide. So first of all, SO2 emissions 6.49 million tonnes. Let's sort out these million tonnes. So a million is 10 to the power 6, so I've multiplied by 6.49 times 10 to the power 6. I've worked out the number of tonnes. I've got rid of the million. 649,000. Or you could put 6.49 times 10 to the power 6 if you prefer it in standard form. And now I'm going to get rid of the tonnes. So the tonnes, a tonne is 1,000 kilograms. So I'm going to multiply by 1,000. So I've got 6,490,000 kilograms. Now I'm going to get into grams. So I'm going to multiply by 1,000 again. So I've got 6,490,000 grams. Again, you can put it into standard form if you wish. So you could have 6.49 times 10 to the power 12 if you wanted. And so now I've got it in grams. So now I can work out the number of moles. Remember, it's got to be in grams for moles, because moles is mass in grams divided by MR. I've got the MR of the SO2 as 64, because I've got a 32 for the sulfur and 2 16s is another 32. So 64, 649,000,000,000,000 divided by 64 is this large number here. From the equation, the moles of calcium oxide has got to be the same, because it's 1 to 1. 1 in front of the calcium oxide, 1 in front of the SO2, so the number of moles of calcium oxide is the same. Then you convert it back again, so moles is mass divided by MR. This is the mass in grams, so this is the moles. Mass in grams I've got to work out. MR of calcium oxide is 56, because the calciums are 40 and oxygens are 16. 56. Multiply this number by 56, and I've now got the mass in grams of calcium oxide. It asks for the mass in kilograms, so if I divide by 1,000, then I come out with 5,678,750,000 kilograms, or I could put it in standard form, something like 5.678 multiplied by 10 to the power of 9.
Question 5. Methanol, CH3OH, is an alcohol with many uses. Draw a diagram show how two methanol molecules interact with each other through hydrogen bonding in the liquid phase. Include all partial charges, that means delta pluses, and lone pairs of electrons on your diagram. So the first thing you've got to do is draw two methanol molecules, so CH3OH, CH3OH, that's your first bit. Then each oxygen has got two lone pairs. Now you can either draw them like this, which is orbitals, or you can put two dots for each lone pair, or two crosses for each lone pair. I usually do two dots, but these orbitals are fine, and there should be two on an oxygen there, and you can put two on this oxygen here as well. But it's the two on this oxygen that are most important here, and as long as you've got two lone pairs on this oxygen, then it doesn't matter if you've not got the 2 lone pairs on this oxygen. Then you need a delta plus and delta minus. Really there should be a delta plus and delta minus on this OH and this OH, but you don't get any marks for this one, it's just mainly this one. So as long as you've got 2 lone pairs on this oxygen and you've got an OH with a delta plus on here, that's fine, because it's this section here that's going to form the hydrogen bond. And the hydrogen bond is the dotted line. You need a dotted line, and that O, H and O should be in a straight line, because those 2 delta minuses, those 2 oxygens, repel as far as possible. And the dotted line should come from one of the lone pairs through to the H on the delta plus. So just to recap, draw the 2 molecules of CH3OH, put the OHO in a straight line, put lone pairs either by drawing orbitals like that, or 2 dots, 2 sets of dots, or 2 sets of crosses. You can put lone pairs on both oxygens if you want, but it's this main oxygen that gets you the mark, and delta plus and delta minus on this OH gets you the mark, although it's good practice to put them on here as well, and line it up OHO. The bond angle around the oxygen atom in methanol is slightly smaller than the regular tetrahedral of 109.5. Explain why this bond angle is smaller than 109.5. It's because you've got lone pairs, so a tetrahedral will be 4 bonding pairs, something like methane. But as soon as you put lone pairs on there, then the bond angle reduces. So if you had 1 lone pair, it comes down to 107, so it goes down by 2.5, 2.5 if you introduce a lone pair, and down by another 2.5 if you introduce a second lone pair and have 2 lone pairs and 2 bonding pairs, right down to 104.5. So what actually happens is it's due to the electron pair repulsion theory. So oxygen has 2 lone pairs, and lone pair repulsion is greater than lone pair bonding pair repulsion, which is greater than bonding pair repulsion. In other words, these 2 lone pairs repel the greatest, and then the lone pair to bonding pair repels next greatest, and then the 2 bonding pairs repel the least. So the 2 bonding pairs get pushed closer together. Methanol is made by a reaction of carbon monoxide with hydrogen. Carbon monoxide and 2 moles of hydrogen react in an equilibrium reaction to make CH3OH. Look, it's exothermic here, so it's minus 91. And look, there are 3 moles of gas on the left and only 1 mole of gas on the right. The reaction used a copper-based catalyst, a pressure of 10 megapascals and a temperature of 550 Kelvin. These conditions are used to provide a balance between the equilibrium, yield, reaction rate and cost. Describe how use of a catalyst and change in pressure and temperature each affect the equilibrium, yield, reaction rate and cost for 6 marks. So you've got to break it down. So how are you going to break it down? You're going to mention that that's negative. That means that going in the forward direction, i.e. the carbon monoxide and hydrogen making the methanol, it's exothermic and gives out heat in this forward direction. Therefore, if by Le Chatelier's principle you lower the temperature of the surroundings, then by lowering the temperature of the surroundings, then by Le Chatelier's principle it's going to oppose that change and try and increase the temperature. So by lowering the temperature, it's going to try and increase the temperature. How can it increase the temperature? Make more methanol, increase the equilibrium yield, or shift the position of equilibrium to the right hand side, because when you do so you make heat. So if you lower the temperature, then it's going to make more heat by shifting the position of equilibrium to the right hand side and make more methanol. However, at a very low temperature, the reaction rate is so slow it would take such a long time to reach equilibrium, so a compromised temperature of about 550 degrees C is used. So by using a higher temperature, that's going to increase the cost than using a lower temperature. Now there are 3 moles of gas on the left hand side, 1 carbon monoxide and 3 hydrogen, making 1 mole of methanol. So the gas on the left hand side take up more room, so they've got a higher volume of the gases on the left hand side. So at high pressure, by Le Chatelier's principle, the equilibrium will shift to the right to lower the pressure and take 3 moles of gas down into 1 mole of gas, because the volume's reduced and therefore the pressure's reduced. And so you're going to get a greater equilibrium yield, more methanol in other words. So a higher pressure gives a faster rate, more particles in a smaller volume, so more chance of successful collisions, and also a greater yield of methanol as the equilibrium shifts to the right hand side. Therefore a very high pressure, 10 megapascals, is used, and that's going to be costly. Creating pressure is costly. A catalyst is used to provide an alternative reaction route and lower the activation energy and speed up both forward and backward reactions, so equilibrium is reached more quickly. It's not going to change the position of equilibrium, but it is going to mean that you're going to lower the activation energy, and a catalyst usually saves on costs because you need less energy, because the particles need less energy to react, i.e. the activation energy is lowered.
Question 6. Propene reacts with concentrated sulfuric acid to form two isomers E and F. The structure of E is shown below. So do a name of the mechanism. So the mechanism electrophilic addition, we'll have a look at that in a minute. So the mechanism, I've done propene here. Prop, remember, has got 3 carbons. You can see the 3 carbons in the product here. And ene means that it's got a double bond. The double bond attacks the delta plus of this polar bond. You've got to remember the structure of sulfuric acid. It won't be given to you. You can possibly work it out from here, but that may not be given to you. You need to remember the structure of sulfuric acid. A sulfur has 2 double bonded oxygens and then 2 OHs. And one of these, remember, this has got hydrogen bonds here, so it's got a very polar bond here, and sulfuric acid will have hydrogen bonds between separate sulfuric acid molecules, because this is a very polar bond. Oxygen is very electronegative compared to hydrogen, so you've got quite large delta plus and delta minuses here. So we've got a polar bond here. The oxygen's electronegative, withdraws electrons along the bond towards itself. That's why it gets a delta minus charge. Now the electrons in the double bond of the propene are going to attack or bond with the delta plus here of the hydrogen, and then the hydrogen's going to bond to the propene. The electrons here, the hydrogen can't bond to the propene and also remain bonded to the oxygen, so the oxygen takes the electrons from the covalent bond and gets a minus charge, and there's the pair of electrons. There's a lone pair now on the oxygen. What actually happens here is that the hydrogen bonds to one of these 2 carbons. How can you remember which one it bonds to? Well, the hydrogen bonds to the carbon with the most number of carbons. So that's one way of remembering where it bonds in most cases. So usually what happens is the hydrogen will bond to the carbon that's got the most number of hydrogens. This carbon's got 1 hydrogen, this carbon's got 2, so it's going to bond onto this carbon that's got more hydrogens. This carbon's got 2 hydrogens, this one's only got 1, so it's going to bond onto here, and I've drawn the hydrogen bonded onto here. That's what's going to happen in most cases. That's called a major product, what happens in most cases. Now this carbon here in the middle hasn't got enough bonds. The carbon is bonded to this carbon here, that's 1 bond, and H is 2 bonds, and also this carbon here. It's only got 3 bonds, and it should have 4. If it's only got 3 bonds, it's short of a bond. In a bond are electrons, so it's short of electrons, it's short of a bond, so it gets a plus charge. So that's where the plus charge is. To balance out the minus charge, remember, we'll make a minus charge because electrons have been dumped onto the O, and that therefore will get a minus charge. Arrow coming this way onto the O means there's a minus charge. I've got to make a plus charge somewhere to balance that out, this minus that I've just made, and that's where it is. It's on that carbon, because that carbon has not got enough bonds. Now, the arrow doesn't come from the minus charge, it comes from a lone pair of electrons. Remember, this lone pair of electrons here is going to be used to form a covalent bond. So it's got to come from the lone pair of electrons, because there'll be a pair of electrons in this covalent bond here. So it comes from the pair of electrons that are being used to bond to this carbon. When it bonds, I've drawn the bond here, and I've got the sulfuric acid now bonded onto the middle carbon. The plus charge disappears. That goes because I've got an arrow coming onto the plus charge. So if an arrow comes onto a plus charge, it removes the plus charge, and if an arrow goes away from something with a minus charge, it removes the minus charge. So that's then the answer there, and that's the major product formed because this hydrogen goes onto the carbon with most hydrogens. We'll explain why that happens in the next part of the question. 6.2. Draw the structure of F. So F is the other isomer. The other isomer is what happens if this rule doesn't happen. In other words, the major product doesn't happen. In actual fact, the hydrogen goes onto the middle one here, the middle carbon, and the plus charge ends up at the end. Well, the simple difference is that this H and this sulfuric acid will be the other way round. So what that will do is the H is now bonded onto the middle carbon and the sulfuric acid has gone onto the end. This is the minor product. This is what's probably not going to happen. A small amount will be made, but it's probably not going to happen. The major product is going to be this one. So why is this one formed. Why does the hydrogen go onto the end, onto the carbon that's got most hydrogens already, and leave the plus charge in the middle, and the sulfuric acid joins onto the middle carbon, carbon number 2, instead of going onto carbon number 1? And the answer to that is here. Explain why more of isomer E, why you get this major product here rather than this minor product here is formed in the reaction. And the answer is that a stable secondary carbocation is formed. It's stable. It's due to the two methyl groups repelling electrons. So what actually happens is, if we go back here, this is a secondary carbocation. A carbocation is something where you've got a carbon with a plus charge, so it's a carbocation. Secondary means the carbon with the plus has got two other carbons bonded to it. If it only had one carbon bonded to it, it would be a primary carbocation. If it's got three carbons bonded to the C with the plus, it's a tertiary carbocation. In this case, the C plus, the carbocation, has got two other carbons either side bonded to it, so it's secondary carbocation and it's stable. If the hydrogen had bonded to the middle carbon, then the C plus would have been on the end carbon, would be on carbon number 1 on the end, on the right hand side, and that would be a primary carbocation, which wouldn't be as stable. And the reason that that happens, if you really want to make sure that you get all the marks, is that the two methyl groups either side of the carbocation, to the left and right, repel electrons and lower the size of the C plus, lower the size of the plus charge on the carbon. You don't need to mention that bit, but you might get, for the second mark, you might need to mention the two methyl groups repel electrons. These two methyl groups here, here, and here repel electrons. In actual fact, as I say, what happens is it lowers the size, the plus charge, and increases stability on the secondary carbocation. So if the hydrogen had gone onto the middle one and the plus had been on the right hand side, that would have been a primary carbocation, which would have been less stable. Just incidentally, the tertiary carbocation is even more stable because it's got three methyl groups surrounding the carbocation, the C plus, all repelling electrons.
Question 7. Propanedioic acid. Propanedioic acid. Prop means 3 carbons, ane means single bonds, di means 2, oic acid means it's got 2 carboxylic acid groups. So it's got 3 carbons with single bonds and 2 carboxylic acid groups. Remember, a carboxylic acid group is C double bond O, OH. It's a solid organic solid that's soluble in water, or the skeletal form of the propanedioic acid. So for skeletal form, you're going to draw dots or corners on a line for carbons, and you're not going to draw any H's, any C2H's. Any C2H's, you leave the H's off. You have to draw the H's on the OH to show that it's an OH and not just an O. So what do you have? You have 1, 2, 3 carbons, an OH, and a C double bond O. So you've got a C double bond OH and a C double bond OH, and you've got 2 of those, got dioic acid, and 1, 2, 3 carbons. Don't draw any H's on. And the carbons, as I say, are corners on lines or dots. Describe how to prepare 250 centimetre cubed of an aqueous standard solution of propanedioic acid. Remember, it's a solid containing an accurately measured mass of the acid. Include essential practical details for 6 marks. So what do you do first of all? First of all, mention it's a solid. You measure the mass accurately of the solid by putting a weighing bottle or a beaker or a conical flask. It doesn't really matter. You can even just say container onto a digital balance and press the tare button. The tare button then imagines that the beaker or the container or the weighing bottle isn't there. So then you're only taking 1 measurement rather than 2, and you're going to reduce your percentage error. So put a beaker or a weighing bottle onto a digital balance and press the tare. Use a spatula to add the propanedioic acid. Remember, it's a solid, into the weighing bottle or beaker or flask until the mass is reached. It doesn't tell you what mass you want, so you just say until the mass is reached, until the desired mass, the mass that you want, is reached. Then you add the contents of the weighing bottle into the volumetric flask. A volumetric flask is a flask that just measures out 250 centimetre cubed. That's all it does, and it does so very accurately. So there's a mark on the flask, and when you get up to that mark, when the bottom of the meniscus gets up to that mark, it's reached 250 centimetre cubed. So you add the contents of the weighing bottle to the volumetric flask. Rinse the weighing bottle, because there might be still some residue of solid in there with distilled water, and add that to the volumetric flask. So make sure that it's all washed out of the flask. Dissolve the solid in the water in the volumetric flask. by shaking or stirring. So shake or stir to dissolve the solid in the water, and then make up the mark up to the 250 centimetre cube on the volumetric flask with distilled water. And then at the end you shake the flask to ensure that the solid dissolves and also that the concentration is equal throughout. Calculate the mass in milligrams of propanedioic acid MR relative formula mass 104.0. Need to prepare 250 centimetre cubed of a 0.00500 mole per decimetre cube solution. So what have you got? You've got a volume and a concentration. So the volume and the concentration you can use to work out moles. So concentration is moles divided by volume. Remember, your volume's got to be in decimetre cubed. So concentration is 0.005. Number of moles we don't know. Volume in decimetre cubed, so 250 centimetre cubed. To take it up into a larger unit value of decimetre cube, you divide by 1000, so 250 divided by 1000 is 0.25. Multiply the two numbers together, so the number of moles is 0.05 multiplied by 0.25, 0.00125. Now moles is mass divided by MR, so we've got the moles is 0.00125 equals mass divided by MR, and you've been given the MR as 104, so multiply those two numbers together. 0.00125 times 104 gives 0.13, but this mass is in grams, so to get it into milligrams, to get grams down to a smaller unit value of milligrams, you multiply by 1000, so 0.13 multiplied by 1000 is 130 milligrams. Propanol can be prepared by the oxidation of propan-1-ol with acidified potassium dichromate. An ionic equation is given. Calculate the minimum volume in centimetre cubed of 0.40 mole per decimetre cubed potassium dichromate needed to oxidize 6.0 centimetre cubed propan-1-ol to propanol. MR propan-1-ol is 60.0. Density of propan-1-ol is 0.8 grams per centimetre cubed. So first of all, if you're given density is mass over volume, so that's the only equation with density in it, so you must have a volume of propan-1-ol, and we do. So we've got a density and a volume of propan-1-ol. So we've got a density as mass over volume, and we've got a density of 0.80 gram per decimetre cube, 0.8, equals the mass of propan-1-ol divided by its volume, which is 6 centimetre cubed. I've left it in centimetre cubed rather than decimetre cubed, because if you look at density, it's got centimetre to the -3, so it's in grams and centimetres cubed. So it's going to give me the mass of propan-1-ol in grams, and the volume's going to be in centimetre cubed. So 0.8 times 6 is 4.8. I've got 4.8 grams of propan-1-ol. Now, what else have been given? I've been given the MR of propan-1-ol of 60. So I've got the mass of propan-1-ol. So moles is mass divided by MR. So moles is mass, which is 4.8 divided by the MR 60. I've got 0.08 moles. Now I refer back to my my equation. 3 moles of propan-1-ol react with 1 mole of, that's the potassium dichromate there, Cr2O72- as an ion. So number of moles of potassium dichromate, 3 react with 1, so 3 moles of propan-1-ol react with 1 of potassium dichromate. So if I take this number 0.08 and divide by 3, 0.0267 is the number of moles of potassium dichromate that I've got. Concentration is moles divided by volume. I've got the concentration of potassium dichromate 0.4. I've got its number of moles 0.0267. I've now got the volume. Volume is 0.0267 divided by 0.4, 0.067, and this is in decimetre cubed. Concentration is moles divided by volume in decimetre cubed. So I've got 0.067 decimetre cubed, and everything is to there's some that are to 3 significant figures, but this one 6.0 centimetre cubed is to 2 significant figures. So even though all of the data is to 3 significant figures, apart from this one that's only to 2 significant figures, you've got to go with the one that's got the lowest number of significant figures in your answer for your answer. So since this 6.0 is only to 2 significant figures, my answer's got to be to 2 significant figures. Turn decimetre cubed into centimetre cubed, because it says calculate the minimum volume of in centimetre cubed. So decimetre cubed down into a lower unit value of centimetre cubed, you multiply by 1,000, so it's 67 centimetre cubed, two significant figures. Complete the diagram to show the assembled apparatus needed to prepare propanol from propanol in this way. Well, we're going to have different boiling points, so you're going to have to, in different boiling points, you're going to have to use distillation. So you're going to have a flask and some kind of bung or a still head with the thermometer in it, a condenser with water in at the bottom and water out, and then some kind of flask. Preferably it'd be cooled as well, so that you reduce the amount of evaporation from your product and increase the yield. But that's broadly the apparatus. If you look, there's a clear flow all the way through. Yeah, there's no lines which are going to stop the aldehyde and the propanol from going up and then down through the condenser. The outside part, which carries water, you have got water in and water out, and water in is at the bottom and water out at the top, and that's sealed round the outside. So let's have a look at what you get the mark scheme. Suitable drawing distillation apparatus with a condenser attached to the side of the distillation flask. You could put a fractionating column here as well if you wanted to, but since you've only got two liquids in there, you can get away with simple distillation rather than fractional distillation. We've got the condenser with an outer tube for water, sealed at the ends, but two openings for water in and out. So it's sealed all the way around apart from water in and out. It's got a downward slope as well. There's a mark for that. Condenser must be open at each end. We've got that. There should be the continuous flow all the way through, as I say, from the aldehyde through here, so that the vapours, the gases, can go into the condenser and cool and come out of the far end. No gaps between joints, so we've got solid lines all the way around, so there's no room for the gases to escape other than to come down into the condenser. Some opening to the system end, and then the condensers labelled. Again, you should have a flask to collect it, and ideally this will be cooled to reduce evaporation of the aldehyde that you're collecting and to ensure that you get maximum yield.
Question 9. The compound 1,2-dichloro tetrafluoroethane is a chlorofluorocarbon, CFC, that was previously used as in a refrigerator as a coolant to cool refrigerators, also used in aerosols and the like, anything that can be propelled out of a can. Very dangerous because they contain chlorine, so now been replaced by compounds that can be used in aerosols and refrigerants, etc., that haven't got chlorine atoms in there, and we'll discuss why in a minute. Molecules of 1,2-dichloro tetrafluoroethane can break down in the upper atmosphere to form chlorine radicals. It's where there's ultraviolet light in the upper atmosphere. Give an equation to show the breakdown of one molecule of 1,2-dichloro tetrafluoroethane to form one chlorine radical and one other species. So what actually happens is that one of the bonds breaks, either this CCl bond here or this CCl bond here, but it's the C to Cl bond that breaks in the presence of ultraviolet light. And what actually happens is the pair of electrons, the shared pair of electrons in the bond, one electron goes back to the carbon and one electron goes back to the chlorine. And to show the electrons have gone one way and the other way as well, we put a dot on each of these two atoms to show that once upon a time those two dots, which actually represent unbonded electrons, have actually been part of a covalent bond that's now broken in the presence of ultraviolet light. So what you've got is you've got CF2Cl, CF2Cl, so I've drawn it as a condensed formula here, goes to, I've broken off this Cl here, but I could have broken off the Cl at the other end. So I've broken this, and this carbon here now has got a dot, and the Cl has got a dot as well. So this bond here is broken, and one of the electrons has gone back onto the C, an unbonded electron here on this C, and an unbonded electron here on this Cl. I could have broken this, so I could have had CF2Cl, CF2 with a carbon, with a dot on the carbon on this carbon here, and a Cl, but I just chose to break this left-hand bond. Give two equations to show a chlorine radical. So these are very, very reactive, these chlorine radicals now. Catalyze the decomposition of ozone. So ozone is O3, so it's a form of oxygen, an allotrope of oxygen, a different sort of way of bonding the oxygen atoms together. Still an element, still O, but got three oxygens bonded together rather than a normal allotrope, which is O2. So it forms O3 can only form O2. There's only two different forms of the element oxygen, O3 ozone and O2 oxygen. Two different allotropes of oxygen. So it forms O2, and then you just got to basically work out what's left over. There's one O that's left over, there's a Cl left over, and there's a dot. The dot is actually on the oxygen, so that's where the unbonded electron goes. Then this is going to react again. Any radicals react again. They're very, very reactive. So OCl reacts with even more ozone. That's why it produces a hole in the ozone layer, because it carries on reacting. O3, the only thing that it can make is O2. A little trick here is that you've got four O's on the left. So if you balance it by putting two O2s, that balances up the oxygen. And then the only thing that's remaining is a Cl dot. Look here, the Cl dot is reformed. It's a catalyst, and no wonder then that by making a small number of chlorine radicals in the upper atmospheres, carries on reacting. This is called a chain reaction, where the Cl dot carries on reacting again with more and more and more ozone, and produces a huge hole in the ozone layer, turns lots of ozone into O2, just from a small amount of chlorine radicals from the use of CFCs. 9.3. Butane can be used as a replacement for CFCs in refrigerators. Good, because it's got no chlorine in it. Good, that won't produce any harmful chlorine radicals. Calculate the volume. So what have I got? I've got a volume of butane gas in 101 kilopascals. I've got a gas constant here. So as soon as I see gas constant R, I'm looking towards PV equals nRT. So let's put PV equals nRT out there. What have I got? So let's start with the butane. So I've got an R is a gas constant. I've got a volume in centimetre cubed. I've got a temperature in Kelvin, and I've got a pressure in kilopascals. So it clearly wants me to use PV equals nRT on this first part here. So let's just do that bit and then worry about the rest of the question in a minute. PV equals nRT, pressure. Now pressure's got to be in pascals. This in kilopascals. So pressure's in pascals. To turn kilopascals down into a lower unit value, a smaller unit value of pascals, and multiply by 1,000. So 101 kilopascals is 101,000 pascals. That's in the correct units now. N is number of moles. Here, can I do anything with that? Yes, I've got a mass here. So I've got a mass, and I've got butane. I can work out the MR of butane, 4 carbons and 10 hydrogens. I can work out the MR is 58, so I can work out the number of moles. I can work out N of butane from a mass, and MR is 0.669. Good. Temperature is in Kelvin, should be in Kelvin. Yes, it's already in Kelvin, so 272. If it was in degrees C, I'd have to add on 273 to convert degrees C into Kelvin, but I don't need to, it's already in Kelvin. Good, so I can just put these numbers in now. 101,000 multiplied by the volume that I don't know. That seems to be the missing value that I don't know. N is number of moles. I'll work that as 0.669. 8.31 is the gas constant. R, I've been given that. Temperature is 272 Kelvin, and I can work all of that out. It's 1512.15. So 101,000 pascals multiplied by volume is 1512.15. Divide the 1512.15 by the pressure in pascals, 0.015. It comes out in meters cubed, so volume is in meters cubed. To convert meters cubed down into decimeter cubed, then I multiply by 1,000. So a large value like meters cubed down into decimeter cubed multiplied by 1,000, that's 15 decimeter cubed. And to get into centimeters cubed, I multiply by 1,000 again to get into an even smaller unit value, 15,000 centimeters cubed. So calculate the volume in centimeter cubed. I've done that. 15,000 centimeter cubed of butane gas. Now calculate the volume of 38 0.8 grams of liquid butane, it's got a density again. So density is mass divided by volume, easy this time. Density is 0.6 grams per decimeter cubed. So the mass is in grams, 38.8 I want in grams. Yes, it's already in grams. And the volume is going to come out in centimeter cubed because density is grams per centimeter cubed. So the volume, rearrange that, volume is 38.8 divided by 0.6, 64.67, and it comes out in centimeter cubed. And then finally use your answers to calculate a factor. That means sort of like a multiplication factor by which butane expands when it changes from a liquid to a gas. So the difference here is I've got this as a gas, I've got butane as a gas, I've got the same amount, the same number of, same mass of butane now as a liquid, and they occupy different volumes. To work out a ratio, which is another word for a factor, I divide one by the other. 15,000 by 64.67 is 232. So it expands, increases its volume by 232 times. I've put it to 3 significant figures because most of my other values are to 3 significant figures 232. Question 10. A drink driving offence is committed if the blood alcohol level of the driver is over 80 milligrams of ethanol per 100 centimetre cubed of blood. What's the concentration in moles per decimetre cubed of ethanol if there are 80 milligrams of ethanol, MR46 in 100 centimetre cubed of blood? So this, so it's asking what the concentration is right on the drink driving limit. Okay, first of all then, what have I got? I've got milligrams, so I've got grams, I've got centimetres cubed, I've got grams, I've got the MR. So first of all, I think what I'm going to do is I'm going to convert milligrams into grams so that I can use moles is mass in grams divided by MR46, which have been given. So my clue is the fact that I've been given MR46 and a mass. I've got a mass and an MR. So that's my first step. If I've got a mass and an MR, I've got the masses in grams instead of milligrams, so to get milligrams up into grams, up into the higher unit value, I've got to divide by 1,000. So if I divide by 1,000, 0.08 divided by 46 will give 0.0017. So my concentration is moles, is 0.0017. Concentration is moles, then 0.0017 divided by my volume in decimeter cubed. 100 centimeter cubed of blood is 0.1, so 0.0017 divided by 0.1 is 0.17. My answer is C.
Question 11 is about Maxwell-Boltzmann distribution curves. Which statement is correct for the distribution curve of molecular energies in a gas? Now I've got two curves here. So I've got one where it's just at a temperature, and I've shown you the most probable energy and the average energy, and notice the average energy is slightly to the right of the most probable energy. And then I've got 3 different curves for cold, medium and hot, and notice the cold gas, the peak, the most probable energy is to the left of the medium curve peak, that's suppose in the middle in energy, and the hot gas is to the right. And notice at a cold gas the peak is higher, medium gas medium, and at a medium temperature the peak is lower. And that's so the area underneath the curve stays the same each time. Notice they all go through the origin because no particles have zero energy, and they should never touch the x-axis again. I notice a couple of the graphs there do actually touch the x-axis, but they should never touch the x-axis again because there's always some particles with a very high energy, irrespective of what temperature it is. So let's have a look which one is correct. 11a, the curve is symmetrical about the maximum. No, it's not symmetrical at all. There's no line of symmetry at all. There are always some molecules with zero energy. No, there are no molecules with zero energy. You'd have to get it right down to absolute zero, which hasn't been achieved, which is not possible for the particles to have zero energy. So there's always some particles with there's always all of the particles have some energy. No particles have no energy at all, so it goes through 0, 0. The position of the maximum of the curve is not dependent on the temperature. No, the position of the maximum of the curve does change with the temperature, and it goes to the right hand side as it gets hotter as you increase the temperature, so it must be answer D. D, the mean energy of the molecules is greater than the most probable energy of the molecules. Yes, it is. So if you look here, the average is to the right of the most probable energy. Question 12. When 1 mole of ammonia is heated to a given temperature, 50% of it dissociates and the following equilibrium is reached. What is the total amount in moles of gas in this equilibrium mixture? So when 1 mole of ammonia is heated, 50% of it dissociates, so half of it dissociates and half of it stays behind. 1 mole would make half a mole of nitrogen and 1.5 moles of hydrogen. So half a mole will make 1/4 of a mole and 3/4 of a mole of hydrogen. So 1 mole of ammonia is going to make half a mole of nitrogen and 1.5 moles of hydrogen. So half a mole, 50% of a mole, would make 0.25, 1/4 of a mole of nitrogen, half of that, and 0.75 moles, half of 1.5 moles of hydrogen, and 0.5 moles of ammonia, remember, remain behind because only 50% of it is dissociated. So if you add all that up, it's 1.5. The answer is A. Which compound is not an isomer of the following compound? So look what I've got. I've got 1, 2, 3, 4 carbons and 1 oxygen. 4 carbons on each of those corners. Now how many hydrogens are on each? Well, each carbon's got 2 bonds there, so there must be 2 hydrogens as well to have the carbon have 4 bonds. So 1, 2, 3, 4, 5, 6, 7, 8. So it's C4H8O. Which one is C4H8O? Answer is D, is the only one that's not an isomer. They're all C4H8O apart from D, which is C4H6O. So the question says which is not an isomer. The answer is.
Question 14. How many isomers are there of C3H9N? There's probably more than you think. So first of all, there's propylamine, so CH3, CH2, CH2, NH2, which is a primary amine. The N is bonded to 1 carbon. And then there's another primary amine where the N is bonded to 1 carbon, but that's 2-aminopropane, where the NH2 is now on carbon number 2, a position isomer of propylamine, or 1-aminopropane. Then you can have a secondary amine where the nitrogen is actually in the chain, so the nitrogen is bonded to 2 other carbons, so you'd have methyl ethyl amine. And then you can have a tertiary amine where the nitrogen is bonded to 3 other carbons, so you'd have trimethylamine. You may be confused and think there's a 5 by putting the nitrogen in between, further along the chain to the left, but all that's doing is flipping it over. The nitrogen is still in between carbons number 1 and carbon number 2. Even if you put it here, it's just that it's other way around. You just mirror imaged it. So there are 4 different ways of drawing C3H9N. Which equation represents a propagation step? Well, the answer is D, because in a propagation step you always get HCl made. So in the first one I've got 2 radicals coming together, I've got a termination step. B is a termination step. C is an initiation step where I'm making 2 chlorine radicals from chlorine using UV light, so the answer is D. Which compound can react with ammonia to produce propylamine? The answer is obviously C, because ammonia is a nucleophile, a lone pair donor, and it will replace the Br on 1-bromo-propane by nucleophilic substitution. Question 17. Which statement is not correct about that chemical? It's got carbon-to-carbon double bond, it's got a branched chain, it's got a Br on there. So let's have a look. It displays EZ isomerism. So EZ isomerism, or geometrical isomerism, which is a form of stereoisomerism, where you've got no free rotation of that double bond, which causes then atoms to be in fixed positions in space. So same structural form, but a different position of atoms in space. The way that you get EZ isomerism or geometrical isomerism is by looking to the left of the double bond and looking at the carbon to the left of the double bond and making sure it's got two different groups bonded to it, and to the right of the double bond the carbon needs two different groups bonded to it, otherwise it's not going to exhibit geometrical or EZ isomerism. So I'm looking to the left of that double bond, and immediately I'm seeing that the carbon has two hydrogens bonded. Those two groups to the left of the double bond on the bonded to the carbon, to the left of the double bond are the same. Therefore, I found my answer straight away. It doesn't exhibit EZ isomerism. The answer is A. Let's just check through then. Forms an addition polymer. Yeah, the double bond could break and form single bonds, and they could add together to make a long polymer chain with single bonds. Reacts with electrophiles such as HBr, yes, it could form electrophilic addition with something like HBr, which could add across the double bond, electrophilic addition. Decolorizes bromine water, yes, it could turn bromine water from orange to colourless, because that's the test for a double bond. Yes, the answer is A. A is incorrect. Which compound can be oxidized to form CH3 twice CHCOCH3? That CO there is a ketone. It's in the middle of a chain, so it's been formed from a secondary alcohol when a secondary alcohol has been oxidized by something like acidified potassium dichromate. So once upon a time, before it was oxidized by acidified potassium dichromate, that's been an COH. It's been a secondary alcohol. The methyl group's still been at carbon number 3, but there's been an OH at carbon number 2 if I start counting from the right hand side. So the answer is 3-methyl. The methyl's there at carbon number 3, but there's once upon a time been an OH on carbon number 2 before it's been oxidized from a secondary alcohol into a ketone by acidified potassium dichromate, and the answer is D, 3-methyl-butan-2-ol. Which species can act as a nucleophile? So a nucleophile is electron pair donor. I'm looking for something with a lone pair, and automatically I'm seeing that oxygen there will have a lone pair. My answer is B. The oxygen on the OH of the methanol has got a lone pair, so it can be a lone pair donor or a Question 20. Which alcohol forms a mixture of alkenes when dehydrated? So what actually happens is when you dehydrate something using something like concentrated sulfuric acid, you remove an OH and you remove an H from a neighbouring carbon, from a carbon alongside the COH. So immediately I'm looking for something that's a secondary alcohol, so that I've got a C to the left and I've got a C to the right, so then I can remove the OH from the middle of a chain, and I can remove an H from a neighbouring carbon to the left and a neighbouring carbon to the right, and end up with the double bond that's produced at two different positions, and end up with two different structural isomers, two different position isomers. So immediately I'm looking towards B and D, and I'm looking towards the longer chain because propan-2-ol is symmetrical. So if I remove the H to the left, I'd end up with propene either way with the double bond at carbon number 1. Let me show you what I mean by propan-2-ol. So if I have propan-2-ol here, if I dehydrate this using something like concentrated sulfuric acid, I remove the OH here and I remove the H on a neighbouring carbon. So the OH and the H here, the water is removed by removing the OH here and the H here, and I'll end up with a double bond here. But because the OH is in the middle of the chain, I could quite easily remove this H to the left along with the OH and end up with a double bond here. So I could end up with pent-1-ene or pent-2-ene. If it's propan-2-ol, then because it's a very short chain, then essentially I'd be making the double bond to the left or the double bond to the right on a 3-carbon chain. I'd end up with propene either way. So my answer is answer D. Which compound has the highest boiling point? So immediately I'm looking for something that's got hydrogen bonding. And here I've found it, hydrogen bonded to an oxygen, a nitrogen or a fluorine. It's answer D. So I've got hydrogen bonding in this propanedioic acid because I've got an oxygen bonded to a hydrogen. I could equally be looking for a fluorine bonded to a hydrogen or a nitrogen bonded to a hydrogen. This fluorine is actually bonded to a carbon here, so I'd get a polar bond, but it wouldn't be as polar as if that fluorine or fluorine and oxygen or nitrogen were bonded to a hydrogen. It wouldn't be quite as polar being bonded to the carbon because there's not quite the difference in electronegativities. So the answer is D. Which compound could not be produced by reacting 2-bromo-2-methyl butane with sodium hydroxide? So I've drawn for you here 2-bromo-2-methyl, so 2-bromo-3-methyl butane. I've drawn it here with sodium hydroxide. So what could happen with sodium hydroxide? It could replace the Br by nucleophilic substitution if I used cold water as my conditions. So I could end up with 2-hydroxy-3-methyl butane. That isn't one of my options. Yes, it is. 3-methyl butanol is another way of doing it. The OH at carbon number 2, 2-ol, and a methyl at carbon number 3. So D could be produced by using nucleophilic substitution of the Br in cold water. So D could be produced. I'm looking for something that could not be produced. And therefore all of the others have made a double bond by elimination. So how do I do elimination? So what actually happens with elimination is that it removes a hydrogen alongside the Br. So the OH minus from the sodium hydroxide removes a hydrogen from a carbon alongside the CBr. So there's my CBr. So it could be one of these hydrogens. It could be this hydrogen on carbon number 1 that's removed. When that's removed, the OH minus and that H will make water. There'll be a double bond here and the Br will be released as Br minus in the elimination reaction. It usually happens under conditions of something like warm ethanol. So I could end up with a double bond at carbon between carbon number 1 and carbon number 2. So I could end up with 3-methyl-but-1-ene, the carbon to carbon double bond here at carbon number 1 and the methyl group at number 3. That's a possibility, 3-methyl-but-1-ene, so I'm going to rule out B. Equally, I could remove this H to the right of the CBr and the double bond could end up here. So if that H gets removed by the OH minus in warm ethanol, conditions of warm ethanol, and the Br comes off, the double bond will be at carbon number 2. So I could end up with 2-methyl-but-2-ene. I'm counting from the other way now. I'm working from the other way. 1, 2, 2-methyl and the but at carbon number 2 as well. So in between carbon number 2 and carbon number 3. So my answer is A. A can't be formed. 2-methyl-but-2-ene. Sorry, the answer is B. Cannot be formed. So the answer is A. 2-methyl-but-2-ene, it should say answer A, cannot be formed. Answer A cannot be formed. Let's just check 2-methyl-but-1-ene. It can't be formed here at carbon number 1 because that would mean that the Br being removed is in the wrong position. That's at carbon number 3. So it can only remove a hydrogen from here or here. It can't remove one of these hydrogens here. So it's answer A. Question 23, I've got an infrared spectrum of an organic compound. So what happens is if you shine infrared light through a sample of an organic compound, then the bonds in there stretch and bend and absorb some of that infrared light. And as they absorb the light, then you get troughs produced. And depending on the bond, they absorb different wave numbers of light as they bend and stretch. So we can identify this. I'm just looking immediately. I've got a very, very wide, broad trough at around about 3,400. That indicates an alcohol. That's an OH group. If it were an OH of a carboxylic acid, it would be further to the right-hand side, just under 3,000 wave numbers though. So around about 3,400, I've immediately got an OH group. What could it be then? I've decided it's not ethanoic acid, otherwise the OH group would be around about 2,800, 2,900. It'd be in the wrong position. So I've got an OH peak here, so it could be hydroxy, that's another word for an OH, or an ol or an ol, so I'm down to B, C or D. As I say, ethanoic acid, the OH would be somewhere here. Instead, it would be around about 2,800, 2,900, something like that. So I've got an alcohol at 3,200 to 3,030, 3,550. I've identified that from my data book. So it's definitely an OH, it's definitely either B, C or a D. Now what's the difference? I've got an one here. I've got a carbon to oxygen double bond. Now carbon to oxygen double bond gives a trough at 1680 to 1750, and there it is. So I've got a C double bond O. I've also, so the answer is B. I've got a hydroxy and an OH group along with a carbon to oxygen double bond. The answer is B. I could also identify that the ene, the carbon to carbon double bond, wasn't there as well. This little peak here at around about 2850 to 3330 is a carbon to hydrogen, so that's a carbon to hydrogen which is going to be in them all anyway. 24. The heat released when 1 gram of ethanol, MR46, undergoes complete combustion is 29.8. What is the heat produced released by each molecule in joules when ethanol undergoes complete combustion? Well, first of all, let's take it one step at a time. I've got a mass and I've got an MR, so let's work out the number of moles of this ethanol. Moles is mass divided by MR. Mass in grams, 1 divided by the MR of ethanol is 46. It's given you, so it's given you a clue, is 0.0217 moles. Now 0.0217 moles gives out 29.8 kilojoules. So 1 mole, if I divide the 29.8 by 0.217, I'm going to work out how many kilojoules of energy would be given out if I had a whole mole. 1 whole mole, and that's in kilojoules. Now this value needs to be in joules, so I want to try and get it in joules because it says in joules there. So to get kilojoules down into joules, then I'm going to multiply by 1000. So multiply by 1000, 1.37 times 10 to the 6, and then it wants to know per molecule. I've got Avogadro's constant is the number of molecules in a mole, and I want it for just one of them, so I've got to divide by 6.022 times 10 to the power 23 to work out the energy given out by just one molecule, and it comes out as 0.228 times 10 to the minus 17, or 2.28 times 10 to the minus 18, which is answer A.